Okay, welcome back, everybody. Follow me. Yeah, sorry for the delay. So as I said, I'm gonna start the lecture first for 1 hour ish, and then we're gonna move to the paper presentations. So quiz. I mean, hope that everybody kind of learned something from the quiz, because as I usually say, quiz is part of the learning. It was a little bit tricky, I know, but the general idea was kind of like, help you to think a little bit deeper about the things that you discuss. I'll share the answer sheet soon, and hopefully we should be able to release the grades soon. Don't be too much worried about your grades, because usually, first of all, the quiz will be 3. It will be only, I think, 30% of your grade. So I mean, usually what happens is that you get full grades and everything else in your quiz would be, the impact of the quiz would be much lower. And I think like if you get somewhere around 75%, usually you get an A in the course. So if I remember, if I calculated some time ago. And I think most of you will get 75, but generally that's the idea. Any questions about quiz? We will have, I think, next one in week 6 or 7, and then the next one in the last week of the class. All right. So last time we talked about, secure execution environments. We get this story up to the place that we said, okay, we are loading our operating system, and then what? And we said that essentially, if we can trust the operating system, then we can ask the operating system to just validate everything that we want to run. But unfortunately, that's not the case in most cases, because the operating system can, one way or another, get compromised. So we kind of need a methodology for trusting the system from the outside, where we only trust that application and nothing else about that program. So the idea is basically, using this reserved part of the memory, which essentially the idea is, we have our general memory. Most of it is actually used by the operating system, and then we use this tiny portion here, which is reserved and can be only accessed by this trusted execution environment, and everything else can be controlled by the operating system, right? And kind of like, any access to this part has to go through this trusted execution environment. And we said that basically this is a similar way that we are trusting TPM, we are trusting the T, and this way we can make sure that the system is not compromised. At least this part of the system is not compromised, so we can trust this part of the memory, right? So that was the overview, kind of like, how the specific trusted execution environment looks like. We said that it essentially starts with this trusted computing base, TCB. This is kind of part of the code that's kind of, burned into the hardware. And since we trust the hardware, we trust this part. Then everything else that we kind of build off of this trusted computing base, we call it dynamic root of trust. Might be multiple different applications, multiple different functionalities. For example, hash function, attestation, things like that. Could be either part of the TCB or could be part of the dynamic root of trust. The reason that you don't want to put everything in your TCB is that, of course, it's safer, but on the other hand, means that you need bigger, memory reserve for your TCB, and that's usually not something that is, first of all, economic, efficient. And then second of all, is something that you can quickly, performance-wise, you can achieve. So you really want this to be as small as possible, really. And you want to, build everything off top of this trusted computing base, all right? And then once you have your dynamic root of trust, which is kind of like functionalities that you need, then you can basically, run this applications one by one. We usually call it secure modules, but just think about it as secure application. Any sort of terminology would work. And you might have multiple of these if you want. We said that essentially secure modules are in communication with some outside user. And when we are saying outside means that the user that is not being controlled by the operating system, right? So usually literally outside, or it could be just another application that is not part of the operating system. And in this scenario, remote does not trust OS, right? So that's the key problem. But the remotes do trust, T. Trust T, right? So that's the difference. And using this attestation protocol, the remote user can actually build a trust on this applications as well. So the default is that the remote trust does not, trust any application. But once we do the attestation and follow the protocol, then the remote user do trust this secure modules. All right. And then we said that essentially we can also have normal apps in the system. Nothing prevents us of running things as we do run before. And these are basically untrusted applications in the view of remote. So remote does not trust these, but that doesn't matter because the operating system might have many other users, and those users might trust the operating system. All right. So this kind of like combination of multiple different users using the same system. And then final thing that we said was this ceiling thing, which was essentially, usually encrypting and plus some math. So anything that we want to store, we usually need to make sure the authentication of the message, plus making sure that only from the inside the system, inside the trusted environment, we can read things and write things. Okay, any questions so far? So once we understood what this is, the next question is, okay, how do we actually build this, right? And we started with TPM, and we said that TPM is basically mostly passive. The only thing that it can provide us and can guarantees us is basically something has been booted in a specific condition that we kind of trust, right? So we can boot things in a known good model. Right? Good state, let's call it. And that's what the TPM gives us. Intel kind of used this idea in order to build what's called the TXT technology. So basically it says that instead of booting the operating system into a known good model, how about using different application and doing that? So instead of booting the operating system, we can boot the system into a specific application, right? And this way we kind of like, we can build a trust. And we can also make sure that only this application has full access to the memory, has full access to the IO, and so on and so forth. And this way we can basically pick that application, whatever that is, and provide this remote kind of capability to remote users. The problem with the TXT was, huge overhead if you want to switch back and forth between applications. And also kind of like, since you're kind of like, making your system a single thread application, there is no interaction between this application and any other application in your system, right? So you're either only operating in this very secure world where you only run this application, or you have to boot the system again, reset the system, and then switch to your normal world. And there is no way of communicating between these two worlds, right? So that's the idea of TXT. And we said that's kind of like, they thought about, okay, how do we make this better? And they come up with the idea of a software guard extension. So you're kind of like extending this guard to multiple different units. And the main idea of the SGX or software guard extension was this notion of enclave, right? So in order to understand enclave, we had like a detour of a little bit of computer architecture and operating system. We talked about virtual memory and physical memory, physical address, virtual address, how we translate virtual to physical, and the page table. And then we said that generally the magic is this in this page table. where essentially the entry, so it's kind of like a line by line based off the virtual address. So the index is basically the virtual address 1, 2, 3, so on. And then each one of these is kind of like have multiple entries. The most important one is the physical address. So we want to go into this table and grab the physical address in order to actually access the memory. But on top of that, there were also these other flags, which usually like, 1 bit or multiple bits, which kind of like, gives additional information about the specific line of the memory. For example, whether this is read only, write only, or execution only, who owns this, who can access this, and all those things. So think about this as just some sort of flags that some metadata that you store with your physical address. And this way we kind of can give the isolation that we want. For example, we can say only core number 1, for example, can access this. And if the request is coming from any other cores, the simple thing is that seeing where this virtual address is coming from, it's just not core number 1. We basically don't give the physical address. And if the other core doesn't have the physical address, they have no idea where this data is actually stored, which means that the other core has no way of accessing data, modifying this data, and so on. And this way we're kind of like achieving the isolation that we want, right? And so this is basically the page table. So the idea of the SGX was kind of separating this page table into 2 pieces. In normal computation, the page table was just one gigantic page table that's been operated and maintained by the operating system. So all the lines are kind of like, in here. We usually have, sub page tables per process, but think about all of these things as one big data structure. That's some of it for process number 1, some of it for process number 2, some of it for process number 3, and so on and so forth, right? For SGX, the idea is that, okay, let's break this down into 2 pieces. One is managed by T. And the other one is just a normal page table that the operating system manages, all right? And then if the data comes in and it's not part of this, basically it has to go in here. And the operating system cannot access this trusted execution environment. Only processes that is coming from the T itself are able to read these values here and do the translation. All right. So basically, anything that coming from the operating system part cannot access things and cannot modify things and cannot translate things. All right. And this way, we kind of remember I said that the memory basically becomes 2 parts, this part here, and then this reserved part here. So basically, this is the part that is being mapped into this page table, and this part is being mapped into this page table, right? So that's basically the idea of creating this enclave. To give you a better idea, this is how it would look like. Basically, your entire VRAM would be 2 pieces. The normal part, which basically this part, and then the trusted parts, which this PRM or physical reserve memory. Within this PRM, we have 2 pieces. The majority of them is this enclave page cache, which essentially this EPC is a page table that has multiple pages. Okay. And these pages can be for one enclave or could be for multiple enclaves. So let's say, for example, these 3 are for enclave number 1. These 2 are for enclave number 2, or so on and so forth. And this way we can actually house multiple of these enclaves on the system. And these enclaves can be isolated from each other, and they're of course isolated from the outside world. Because only trusted execution environment can access this, which means that only trusted execution environment can access this specific pages. Okay. Any questions so far? Okay. So this is just, to give you just what I just said. So basically we divide the memory into regions. We store the translation in a secure table that is managed by the trusted execution environment. And the main thing is that the SGX hardware is actually the ones who is responsible for creating an enclave and deleting an enclave. All right. So now the next question is that how do we actually create a new enclave? So if you want to load things and start things, how do we do that? The most important things to remember is that the SGX is the one that is who is responsible for creating the enclave for you, and this is kind of the steps that we need to follow. The first is we need to create a new enclave. But remember, remote user does not trust anything about us, about the system, right? So we need to kind of show some guarantees, give some guarantees to the remote user that this trusted enclave environment is indeed what it's supposed to be, right? So the environment is basically just think about it as a piece of code, right? So it's a list of functionalities and APIs and so on, some libraries. So what we need to do is basically showing the remote user that indeed when we are creating this enclave, it's an enclave that we can trust. Okay, how do we do that? This is the protocol that we usually follow. Right. So this is the remote user, and this is the hardware. Right. So the remote user does not trust this, but trust the T inside. Okay, so how does this format works? So there are things inside this trusted platform that the remote user do trust. There is one thing that the remote user do trust, and that's the attestation key or a key. The attestation key is literally a key that's been burned into the hardware, stored into a secure memory of the hardware. There's another thing called endorsement certificate, which basically just saying that, it's kind of like, digital signature, which basically saying that this is coming from this hardware. So think about Intel as a manufacturer, and whatever Intel builds, they actually sign this and put the endorsement inside each of these hardware. So if this hardware present this endorsement certificate, you can always check with Intel to make sure that this is actually the hardware that they have produced. All right. So the idea is that the Intel sign it and put the signature into this certificate. In order to verify this is indeed signed by Intel, you get this certificate, you go and check the public key of Intel, and if this indeed can be verified, you can say that, okay, this is actually the hardware that we can trust. Okay. So basically, you trust Intel and you trust the public key of Intel, and this way you can trust this endorsement certificate. All right. So let's see what's with these two things that it do trust. Questions?
What does HCO stand for?
Say it again.
HCO.
Where is HCO?
Oh, sorry. I thought
this one?
Platform. Yeah.
This is hardware.
Oh, okay. Sorry.
Yeah, hardware. Yeah, sorry about that. Okay. So we have these two things that we can trust. So let's see how it works. So the remote user wants to create a new enclave, right? And let's imagine this is the enclave that we are talking about. Let me use another color. So this is the enclave that we create. So the hardware, so we send a request from the remote user that creates a new enclave, create a new enclave for me. And the hardware going to create this initial state in code and data. All right. And this is just a public knowledge of like what is the initial state of an SGX. You can actually, this is again similar to the way that we create AES or RSA and so on. This is usually public information. All right. So what we need to do is that in order to build the trust that this is indeed not modified and this is something that we can trust, we need to provide an attestation of this piece of code to this remote user. So this remote user now is the verifier. And this part of the code is prover. Remember, we talked about attestation. We have a piece of code. We want to show to some remote user that this code has not been modified. What we did was we basically, the verifier sent some sort of a challenge, which basically saying that, compute the hash function of this lines of memory and send me back the hash function. I'm going to compute the hash function locally, and I'm going to compare these two, right? This is exactly the same situation. In this case, this remote user does not trust the hardware, and this part of the code needs to be attested, right? So how should we go about this? This is two steps that usually we go about this. First, they need to agree on a key, okay? And in order to agree on a key, they usually follow this protocol called Diffie-Hellman, but they can also use things like, hybrid encoding, hybrid encryption, and so on and so forth that we discussed in the class. The simple thing in order to create the key exchange is basically the remote user creates this G to the power of A, send this G to the power of A. The remote user going to create this value B and going to compute this G to the power of AB. So basically whatever GA it gets it to the power of B and then send it back. And this actually becomes their shared key. And there is actually, a mathematical, proof that this way, nobody other than this user and this user can know what the key is, okay? Because this user has the access to A and does not have access to B, and this user has access to B and does not have access to A, and nobody in between sees both A and B together. And this way, G to the power of AB becomes the shared key, but nobody else knows what that key is, okay? So that would be the idea of exchanging the key. Yeah.
Does the transfer of G of A needs to be secure, or it can be exposed?
It could be exposed, right? That's the idea. So the attacker basically only sees G of A. It never sees anything else. So it sees G of A, sees G of B, but not both of them at the same time. Okay, so once we have that, but again, this is not a part that is important for us. The part that is important for us is that these two, after this protocol, agree on the key K. Okay, how do we get it? It's a different story. So once we have this key K, all we need to do is basically compute this hash value, and we call it M. And then we also sign it with our attestation key. We're basically saying that this hash is coming from this hardware here. It's not something that some other user in the middle of the computation send it to us. So two things that has been sent to the remote user. One is that this hash has been computed from this hardware, and this is achieved by signing it with the attestation key. And the second thing is the actual hash value itself. So we send the hash and we send the signature of the hash, okay? So two things has been sent here. And here, basically, I haven't shown it here, but the remote user also computes the hash here and gonna compare this M with this H, basically. If they matches, and if it verifies that the signature is also coming from this user, then it's the time to actually do trust this server. Okay. Any question here? Okay. And then once we have that, so once we can trust this user, now it's time to actually send the actual code and data that we want to execute. Remember, for now, the only thing that we attest was the initial state of the enclave, right? Just a bunch of APIs, just a bunch of initialization functions, and so on. Remember, what we want to do at the end of the day is being able to run some application on this hardware, right? So we have an application on the remote device. And what we want to be able to do is that run this on the T, right? And this way, we basically, once we trust that there is actually a trusted enclave inside this T. Now it's time to actually send this value, this application to the T itself. So we're gonna send this, and that would be this. Okay, and we don't send it in the clear. We don't send the plain text because we can consider this as secret. So some of the data that we send or some of the code that we send might be secret. In this case, we're going to encrypt it with the key that we actually agreed upon. All right, so this is the key that we actually agreed upon, and we're going to encrypt this and send it. All right. And what happens that afterwards, this is basically just a normal execution of that code. So this is where we actually do run things. So this is the most time consuming part of the protocol. We compute the results, we encrypt the results and send back the results. We decrypt the results and we have the results. All right. So think about this application as f of x equal to some y. So we send basically f of x here. We get y, encrypted of y, of course, and then we decrypt y and we get y and we are done, right? So that's the whole process. Let me repeat it one more time to just get an idea of what's going on. So we have this remote user here. We have the hardware here. Inside the hardware, we don't trust anything. So anything that we want to execute in this hardware needs to provide some guarantees to the remote user. The first thing that we're going to do is that we're going to send a request that creates a new enclave for me. The hardware going to create this initial, states and code for us. In order to prove that this is indeed a trustworthy piece of code, we follow an attestation protocol, which essentially this part of the code here going to be computed by a hash. The hash function of this is going to be sent to the verifier, to remote user. The remote user, since this part of the code is public information, public knowledge, they have a copy of this here as well. They can actually also compute the hash value of this, compare these two hashes and make sure that these two hashes are agreeing with each other. If that's the case, it means that this part of the program can be trusted and we can just move on to the next phase of this protocol. Additional things that needs to be done is in order to make sure that this indeed is coming from this hardware and not any other hardware, we need to sign this hash function, right? So not only we send the hash, we also sign the hash and send the signature of the hash. How do we sign the hash? We use the attestation key that is already in that hardware. And in order to verify this hash, we ask Intel to give their public key. Their private key is basically this attestation key. And remember, we said that if you have the public key and you have the signature, you can verify it. So that's the idea here. So we have the public key, getting it from Intel. The private key is already inside the hardware. The hardware used the private key to sign it, sends us the signature. We have the public key, signature, verify it. Now that it's actually indeed from this hardware. All right. And in this process, the additional thing that we do is the key exchange. The key exchange, again, is not something that you need to be worried about too much. It's just a way of these two agreeing on a specific key. And since we are kind of like, every time that we create a new enclave, we need a new key. We cannot just burn all this key inside the hardware, right? So we need to create this key dynamically. And that's why we do this key exchange. Once we have that, we are happy at this point. And now it's time for us to send our code, our secret code and the secret data to the hardware. The hardware gets it, decrypts it, start executing it, and send us back the results. Again, encrypt it, we decrypt it, and we are getting what we want, right? And this process can forever, moves on and on, right? We can create more enclaves, we can destroy enclaves, and so on and so on. Is that clear?
So how exactly do they generate the shared key from the part that gets transferred publicly?
So again, this is what's called a Diffie-Hellman key exchange. If you're interested, take a look. But generally, the idea is that one of them creates some sort of local secret, which is A. The other one creates another local secret, which is called B. And then each of which they kind of power it to the power of GA, and then provide that results. The reason that this is secure is based off some hard theory called discrete logarithm problem that essentially says that if you see G and A, so you can basically, if you see GAB and GB, you cannot find GA. That's usually the idea.
Is the hardware attestation key based off like the serial number or something? Because
Yes, it's based off a serial number. So basically, it depends on how Intel creates this. Usually, what Intel does is creating one public key for multiple secret keys. That's one thing that they can do, or they kind of like have a giant table of saying that okay, this device has this secret key and this public key and so on. And then you can always query Intel for that.
I see. Okay, thank you.
So when the key exchange is complete, we use the magic key for encryption.
Yes. So basically, this is just a way of. Another way that we could have done it was using some sort of public and private, and then use that in order to achieve that. But that's another way of doing it. Are we good? All right. So we kind of like talked about this part, and then essentially, if there is some sort of context switching happens, the actual operating systems, deal with it. But something that to be very careful is that since we have non-secure applications and secure applications, right? So we usually call it secure modules. And if we run this back and forth, we need to be careful when we are switching from secure to non-secure. We kind of like need to remove the sensitive information from the system, right? So usually if you want to destroy a secure module, or we want to switch back to a normal non-secure module, what we need to do is basically making sure that the information about the page tables and things like that are deleted from the system. So in other words, we need to make sure that the operating system cannot access those information, okay? So there are some operating system level details about this that we kind of gonna skip, but just have this idea that, switching back and forth between something that is secret and non-secret requires some sort of cleanup. All right, so we need to clean up the registers, we need to clean up some of the cache and so on and so forth. All right, and that's usually taken care of with the trusted execution environment. Okay, new question here about SGX?
For enclaves, there's like a shared library that from the operating system. But it's just like loaded separately.
So enclaves can usually access things on the operating system side. So if you have a shared library that we need to use, we can basically put it into the non-secure part of the memory. And the secure part of the memory can always access and read these things. We don't trust we trust the secure part, we don't trust the non-secure part. So secure part can actually do access those non-secure parts. That's fine. And then they can also share something in between them. They can share something between non-secure and secure. So there is also like kind of like, as you will read the papers for this topic, you will see that the original SGX was pretty limited, but the people start thinking about, okay, how to improve this, how to make this much more easier in terms of performance. So if you want to share in a very specific way, how we can do it and so on. So it's just adding more features. It's something that people are working on these days. Okay. So of course there are some limitations with Intel SGX. So handling interrupts and I/O, since we kind of like need to switch back and forth between normal board and secure board, that's something it's a challenge. Another challenge is the performance itself, because we essentially what we do is we kind of like reserve only a very tiny portion of the memory, and in that case you cannot have giant enclave application, because the best you can assign for any enclave is this a small amount of memory. So workload that needs huge amount of memory cannot be executed on enclave, and as a result, you don't get the best performance out of the system if you want to run something that's heavy. And that can be a problem for some class of applications, and especially if you're dealing with the IO and so on and so forth. So that's why once you read some more papers, especially those 3 papers that we assigned to you, we'll see that there are some discussions of how we can improve the system based on that. Okay, and the final things that is actually one of the papers that you will read is this system is secure with this assumption that there is not sort of what's called a side channel, digital side channels. And you will see that, actually from this normal word, you can create some faults, you can create some activity that impacts the system here. And as a result, they actually can leak some secret. Because essentially what SGX does is just kind of isolate the mapping, right? At the end of the day, this is physically shared between non-secure word and secure word. And the only thing that kind of isolating is the mapping between those two. So we're saying that, this mapping, this is the part that we kind of making it secure. So it's kind of like a gateway to that memory system. Is that what we are keeping secure? The actual memory system is still shared between the user and all the malicious and adversarial users. And in that case, there might be some ways that the adversary can actually change some physical aspects of the system in order to attack the system, right? So if we had true isolation, in another sense that we have 2 pieces of memory that literally physically are isolated from each other, then we would have much more secure systems. But unfortunately, because we only, for example, have one die of the memory or one slot of the memory, we need to physically share T applications with non-T applications. And as a result, there are physical attacks, false attacks that the attacker can launch in order to impact our systems. And you're going to see one example of this in your paper reviews, okay? So it's very important to know that, things that we do, we digitally, separate these things, but in reality, we cannot really separate them because we have constraints such as cost, has performance, has area, and these kind of things, all right? Okay, so that's it with the ARM Trust Zone. With Intel SGX. There are other applications, there are other options for trusted execution environments. That's also important to know. I'm going to go quickly over ARM Trust Zone. There's some other as well that I'm going to probably skip. So Trust Zone, the main difference between Trust Zone and SGX is that Trust Zone is making things much more lightweight. And the reason for that is, Trust Zone is usually used at the mobile or more embedded system level computation. So they're trying to make the hardware circuitry, the features a little bit simpler and easier. As a result, the way that ARM Trust Zone is basically giving us this trusted execution environment is dividing the word into 2 parts, the trusted part or T part and the normal part or V part, all right? And instead of having, enclaves, small enclaves, as you remember, we said that we basically can have multiple secure modules and then have, multiple normal application in SGX. Trust Zone is basically this model of things are either in the secure world or in the non-secure world. And there is no isolation or differences between applications in secure world. So basically this application can access things in this application and can access things in this application, all right? So there is no separation between page tables or all those things in Trust Zone. Basically what it does is basically saying that, okay, things are either trusted or not trusted. If they are trusted, they can share the same hardware, they can share the same memory and so on and so forth. And if they're not trusted, they can, again, share the things between themselves, but these 2 cannot share things among themselves, all right? So that's the biggest difference. And usually what it does is it has what's called a secure operating system or secure OS. And it also has what's called a rich or regular OS. The regular OS is what we usually have. And when we are saying rich, it means that it has more functionality than our secure OS. And in order to kind of like, handle this switch back and forth between normal and trusted, we have this additional thing called secure monitor. So this is basically was our T hardware in SGX. So what it does is basically it's a piece of hardware that kind of orchestrates everything. So the green here is the part that we trust. So we obviously trust the secure hardware, the secure monitor. The secure monitor builds the secure operating system. The secure operating system basically manages and handle all the applications in the trusted domain. We also launched the rich OS, the normal OS, but obviously we don't trust the normal OS. And as a result, we don't trust any applications that's been interacting with the rich OS. And the guarantee that the trust zone gives us is that none of these applications from this left side can actually access anything on the right side. So this will be blocked using the secure monitor. But these things can actually, talk to each other and share things to each other. These things can share things to each other, but not across the trust domain. Okay? Any question here?
So can the secure applications access stuff in the rich OS or no?
Sometimes they can access some of the things from the rich OS, yes. But usually that goes through the secure monitor and go back up to the rich OS. But again, the problem with trust zone, as we're going to talk about, is most of the things needs to be handled with the secure OS, and that creates some limitations because not everything can be part of the secure OS. Otherwise, the secure OS would be so big that we cannot really trust anymore. Okay. Any questions about trust zone here? So let me give you a little bit more details. So the implementation of this normal word and trusted word or secure word is basically based off two hardware features. There is the first one is what's called the AXI bus interface that basically enforces the control. So what it does is basically we are augmenting each memory access with additional bits that says that whether this is secure or not. So if, for example, if it's 1 is secure, if it's 0, it's not secure. So whenever we are reading the memory, we want to send some request, either reading or writing to the memory. We need to send this bit with it. And then basically the secure monitor, so the memory will be sitting here. So any request that is coming from this side or this side has to go to this AXI interface, and it has to check whether this bit is equal to 0 or equal to 1. If the bit is equal to 1, it means that it access the secure part of the memory. If the bit is 0, it means that it cannot access that part of the memory. All right, so very simple. So it doesn't need to go necessarily through page tables and those kind of address translations. Everybody has their own 1 bit, and they can use that 1 bit to show that whether that's 1 bit can be can access the secure memory or not. Okay. So and then this is basically enforced by AXI, and of course only secure monitor is able to change that 1 bit. So the normal applications cannot modify their own bits, obviously. Otherwise, normal word application can mimic themselves and show themselves as secure applications. So secure monitor only set that bit, and the bus interface basically check that bit. And if that's bit is equal to 1, then it's safe to access the secure memory. Okay, so that's number 1. The second thing is that since we are kind of like running things back and forth between secure word and the normal word, what we need to do is kind of like context switching between the two. All right. And because we usually have only one, core for running things. And this time slicing is actually done via the secure monitor here. So we have one app, let's say we are running this app for some time. Now we want to switch to the trusted app. So the request goes into the secure monitor, goes in here, and now we start executing the secure app. Once the secure app is done, or for some reason we need to switch back to the regular app, again, the request goes into the secure monitor. The secure monitor needs to do some cleaning because this and some part of the memory might be in cache, and those information might be secure. So we need to do the cleanup. Then we switch back to the normal app and we execute. All right. So basically, the secure monitor is something that sits in the bottom of our trust, and any sort of interaction has to go to the secure monitor. So the secure monitor gives access to who goes next, right? Think about it as an intersection, and then there's some police officers that tells who comes next and who can turn right, who can turn left, and so on. So the secure monitor is basically that officer in this case. Any questions here? Okay, so this is basically on TrustZone. We have two different boards. The boards kind of interact with each other through the secure monitor. In order to achieve security, we have this additional 1 bit that kind of tells whether you are secure or not secure. That 1 bit is being enforced and monitored by the AXI interface, which is the bus interface between the core and the memory. And then the time slicing between running things in secure board and running things in normal board is being handled by the secure monitor. Okay. And basically, so in order to initialize the system in a secure manner, what we do is that we boot into the secure board. All right, so we first boots the secure monitor. The monitor then invokes the secure OS. The secure OS then invokes the rich OS. All right, so we kind of trust this, then trust this, and then since we trust this, then we can load the rich OS. And at that point, we no longer trust the rich OS anymore because it might or may not be trusted. All right. And then there will be all the APIs that we discussed in SGX, including the sealing, including the attestation, the key exchange, the encryption and decryption, and all those things. So all those things still the same. So again, if somebody remotely wants to execute something, the secure OS has to do the attestation for them, provide the security guarantee that this indeed is not being modified, and so on and so forth. All right. So all those things that we talked about, the protocol that we talked about the attestation, and actually the same thing happens here. Okay. So that's kind of the story with trust. Yeah.
If you have hardware virtualization, does it come before the secure OS? So like, do the VMS instances share the secure OS?
So most of the virtualization and the interaction is actually done at the monitor, at the secure monitor level. So what happens if you boot the system and all the virtualization, I mean, any sort of initialization for that is done at the system, the secure monitor level.
So each instance.
The secure OS is just mainly for managing things at the secure board. So things like attestation, things like encryption, decryption, things like that. That's what's being booted at the beginning. Okay. Are we good? So the obvious problem with TrustZone is there's only 2 modes, right? So you cannot really, add additional SGX-like behavior in TrustZone. Part of it was intentional, and part of it was just at that time they thought that this would be good enough. There are, as I said, there are works that tries to build off of TrustZone in order to make it more interactive. One of the papers actually would be about this. But very recently, ARM itself created this new thing called CCA, Confidential Compute Platform, something like that, which is kind of like, think about it as TrustZone 2.0, which basically kind of gives the SGX enclave-like behavior for ARM Trustzone as well. So nowadays, the next generation, actually, I don't think there's any device right now that use CCA, but the promise is that you can now have multiple different secure applications in the secure world and so on. So kind of like, CCA becomes very, very similar to Intel SGX in some sense. Okay. And the biggest problem with just having two words, obviously, is the fact that, all the applications in this secure world has the same type of privileges and accesses, right? And this is in contrast with what we discussed before, that principle of least privilege, just because essentially some of these applications here does not necessarily need to have access to many different things, right? So what you want to do is being able to create these isolated enclaves that are kind of like, isolated from each other. But as I said, Trustzone cannot provide it as it is. Future generation do provide that capability. Okay. So that's it. So there's other ones, including Sankis, but I think we don't have much time to talk about it. So I'm gonna just skip it. But this one is basically like, the idea is that even going more lightweight than Trustzone. So doing something very, very basic. All right. So if you're interested, just take a look. But I mean, we are assuming that we're just skipping this. There's also many other options, including Keystone, Sanctum, and so on and so forth. And just the difference between them is kind of capabilities and being lightweight or more heavyweight, right? So for example, if you want to have very, very simple thing that's just making sure that one application is being executed securely, then you can have a very limited, amount of changes into your hardware in order to achieve that. Because remember, when we are talking about these things, we are talking about secure monitor, we are talking about secure OS, normal OS, and all those things. And these are all additional overheads, right? Because in normal execution, we only have this normal OS. But when we are adding things like secure ARM Trustzone, we are adding this and many other additional functionality. This means additional hardware, this means additional power, this means additional area, and so on and so forth. So the cost and power consumption, all those things goes up. So what you want to do is being able to achieve some of these functionalities, but not at the cost of this huge power overhead, right? So that's kind of like the story of all these other methods that's trying to achieve kind of like, best of both worlds in some sense. Okay. I guess I'm going to stop here. And we don't have to go through these other things. Then I'm going to probably just, skip this and remove this from the slides. And then we're going to talk about one last thing I want to talk about before we actually move into the paper presentations. So remember we said that, for T, two applications that we really care about. One was trusted computing and the other one is confidential computing. The difference between these two is that trusted computation, as I said, we have an operating system and we don't trust this operating system. There was this remote user that some way needs to trust this operating system, right? And with Enclave and the secure, enclaves, you basically create this enclave, you provide proof to the user and say that, okay, now send us the code and data here, right? So that's what we usually do. Similar idea, but slightly different, is what's called confidential computing. So the idea here is we don't necessarily not trust the operating system, but because of privacy reasons, we don't want to share our data. So for example, let's say there's a hospital that has some patient data, okay? And we want to use a very sophisticated server somewhere in the cloud, let's say Amazon Web Services, AWS. And AWS has this very high-end machine learning classification algorithm for detecting disease of patients' data, right? So we have this very high-end machine learning model in the AWS. If the hospital wants to use that model, two options, right? One is that we either put this ML model inside this data, this hospital computer, and then do the computation. The problem with that is AWS may not want to actually share that machine learning model because it's part of their IP. They want to actually earn some money from it, right? So the other option is that the hospital sends their data to the AWS and say, okay, classify and label this data for me. But there are some sort of privacy issues with that. HIPAA, you may not be allowed to share your patient's data to a remote agency, right? So in this case, what we need is what's called a confidential computing or privacy preserving computation, which essentially we have part of data that cannot be shared with the outside world, but we have some computation capability that we want to use. How do we do that? There are multiple different versions of this that we can achieve. We're gonna actually talk about it later, but trusted execution environments is very, very interesting solution for this. Because remember, when we said that essentially after all these things, we're gonna share our secret code and data to the enclave, and only enclave is the one that has access to this information. That's exactly where we can use confidential computing here, right? Because we don't trust this hardware, but we do trust this trusted execution environment. And as part of this trusted execution environment, we can make sure that once we run this machine learning model, once we get the results, everything else will be destroyed. So this user only gets the results that he wants, basically the classifications of their data, their patient data. And this hardware, which basically in this case is the AWS, never sees the actual data. It only sees the encrypted value. The encrypted value will be decrypted inside the trusted execution environment. And since we trust the hardware, we can trust this system. So in other words, the operating system, the operating system of the general cloud never sees the actual data. The data only will be seen within the T when we decrypt it. And since we trust the hardware, we trust that process itself, right? So this way we're kind of achieving what's called confidential computing. To learn more about it is actually one of the 3 papers that you're going to be assigned this week is about that, why we need confidential computing. There are some interesting example there. And they also showed that how this can be achieved using Intel SGX. Okay. I guess that's it for today. Rest of it, we're going to talk about paper presentations. So let's start with the first group. Are you guys the first group? Yeah. Okay. We can have like a 2 minutes break as well. You guys can come and set up here. You have your slides on.
Share it with me.
You emailed it to me, or what did you
Yeah, I
do?
should.
Yeah, we shared it and we put it in the Google Drive.
Oh, all right, guys. Yeah, go ahead.
Wait,
Should we full screen?
Yeah.
And then just make sure that this follows you.
Wait, where is it?
Oh, it's there. You just do next. What do you want to do?
Like full screen.
Oh, full screen.
Yeah.
Should be on. You want to be the slide with it?
Sure.
Yeah, it's just fine in there. Go up.
Oh, I see it.
Yeah.
Okay,
There you go.
perfect. Wait, is it just this? Okay.
And then just do this, so this camera follows you, whoever speaks. No,
Oh.
like your hand like this, it will be blue and then green. Does it work?
Oh, yes.
Okay, cool.
Okay. Hi, my name's Emily,
What's your idea?
and we were the first paper for this week.
So getting right into it. What is the problem that our paper is trying to solve? First, we need a little bit of background. So ICS is an acronym for Industrial Control Systems. And these are systems that control large-scale infrastructure in healthcare, electric grids, manufacturing. And these are controlled by these devices called programmable logic controllers, or PLCs, which are these little blocks that run, basically just run code that controls the entire system. And so that leads to a large vulnerability in that if all of our infrastructure is based on code running on these devices, those devices have to be secured. So what is our threat model? Currently, the threat model for these PLCs is actually that attackers can use the network to change code on the devices by either injecting it, removing it, modifying it in a way so that they can either get information out of the system. So like a healthcare system, they can get sensitive information about maybe patients, or an electric grid system, maybe they can shut it down, which Emma will talk about some examples actually. Well, actually, first, there are companies that do analyses on ICS vulnerabilities. So this is one such company called Clarity, and there's actually like 50 plus like main vendors. You might have heard of Schneider Electric, which is a main one. And a lot of these companies care about the vulnerabilities in their system because they're providing access to resources to so many people around the world. And so it's important that we maintain security in these large scale infrastructure systems.
So why is this a threat? So in the research paper, a big thing that they talked about of the problem that they were trying to solve was port scanning. And basically what this happens is that like you can scan to see which ports are open. And then by being able to see the open ports, you can see like where data is being sent and received, which creates vulnerabilities for all of the different servers and networks that are using these ports, because then it gives the attackers basically the perfect location and the perfect like positions to attack these networks. And such examples, there were two really big ones, but as you can see in the previous slide, there's a lot of smaller scale issues that the report, the previous company talked about. But some of the really big ones that were mentioned was Stuxnet and Black Energy. And Black Energy was actually an example that happened a few years back, where this was a nationwide state attack. And what happened is the main PLC was attacked. And because the main one was attacked, it actually took out 30 different substations. So we can see that this is like a huge issue in terms of like privacy and like safety of like people and all of the information that's being stored. And then the solution is what the paper ultimately talks about, which is Zeus. And they model it and name it as a contactless embedded controller security monitor. So the reason that it's contactless is like just like basically by the name is that it's non-intrusive monitoring of PLC. So I'll go into that more later, but they basically first can identify all of the different instructions, and then by monitoring the current instructions that happen, you're not actually intruding into like any of the port scanning or pausing it or anything like that. And this also, the main thing is that it eliminates like infections like of monitors, and it's like very secure because they keep control flow integrity. And the monitoring, again, this is like what was written in the paper that you all read about, or some of you read about, and we'll go more into the details of that.
Yeah, so this is just like a block diagram. The lightning bolt is kind of misleading because usually lightning goes from the top to bottom, but actually what we're doing, what the papers do, is that a sensor is going to record the electromagnetic radiation from the PLC. So the device has some transistor switching in it, which will create some electromagnetic field, and that will be monitored by the sensor and captured. And then the Zeus platform actually takes that data, runs some machine learning models on it, and checks if the signals coming out of it are actually not malicious, like can detect like malicious intent or code changes, or if the actual signals are like the golden model or what should be happening on the system. So the setup that they used is actually, they just took a microphone and took out the transducer, which means the microphone just takes, a transducer takes like a mechanical vibration and changes it to electrical. But instead, they just took the mechanical to electrical part out. So they just basically just monitor the EM field directly from the PCB, like the circuit board on of the PLC. And they went around, they checked different parts of it to see where the main signals would be coming from, and then just put the microphone right next to it, captured the signal with an oscilloscope to see if like they're getting farmer signals and later fed those signals into their platform to train it. Oh, and one more point on that is that if you monitor these signals in the time domain with an oscilloscope, you'll actually get a lot of noise that you won't be able to tell about. You want to be able to differentiate. But what they did was they looked at frequency domain data, so we could actually delete out low frequency noise and just look at high frequency to see where the actual that their important information is. Yeah, so the execution environment was actually on these Allen Bradley. The company makes like a lot of North American PLCs, and so they tested on them because it's a common thing. So that means the paper is the most like versatile to use. And so they ran all their tests on those, and they used main control programs like PID, AES, gradient descent. These main like algorithms that we've all heard about that are going to be consistently used in these systems, right? So if you test it on consistent popular algorithms, then this system can be used in basically other systems that use this one.
So going into their actual control flow and integrity monitoring, you can see this is a diagram from the paper. But to go just more a little bit into it, they have like two main stages, but the main stage is the deployment stage, because in the training stage, all they do is they actually collect all of the traces and they transform them into these like spectrum sequences. And that's like the first step. They just like collect all that data. And then once they have this data, they use a lot of like the machine learning, like that they talked about later on in the paper, such as neural networks and things like that. And they create a program behavior model. And they do this by like, they create a train model from the spectrum sequences. And this creates a probability distribution from all of the different classes, because they did a lot of testing, which is one thing that was really good about this paper, is they tested over a bunch of different models, like different instruction mixes, and they combine everything into the probability distribution. And then to actually see which data could be like malicious and not part of the actual program, what they do is they take the classes from this probability distribution and they see the highest score, and that's like the threshold. And then from there, they have the threshold checks, and that's how they're like actually able to see what the malicious data is. Because if the threshold check fails, then we see that there's like a mismatch in data, which then what Zeus does is like they also create a much more intense like report, and they for instance, they create like detailed reports about how they created the vulnerability, and that also prevents it from happening in the future. And then this is some more of the experiments, like you can see just like pointing out the different things that they have, like the FPGA chips. And above here is, as you can see, the different instructions that they tested. Sorry, there were like two pictures because they actually tested like double this amount of instructions. But as you can see, this is just the way that they ran the testing, and the results you can see here. The main thing that the paper talks about is that they were able to detect malicious code injections with 98.9% accuracy, which is extremely high. And the main reason that they were able to do this is because they, as you can see, like the instructions that I showed before, by being able to identify the instructions at a really high rate, they were able to see like, oh, like is what's happening on this network supposed to be happening, or are these like instructions coming out of nowhere, meaning it's like someone trying to get into the system. And as you can see, like also if you want to talk about the likelihood score.
Yeah, so one interesting thing actually about this is that they tried two different models. So they tried a hidden Markov model and they tried a long short-term memory model, which is like a neural network. And they found that the hidden Markov model actually works like faster because it runs faster than the long short-term the neural network model on their Zeus platform. But the LSTM actually gets higher accuracy. So they had to work on this trade-off between picking a system that can like detect quickly or detect more accurately. And so you can see that the neural network model is more accurate. And then in terms of the likelihood scores, they in each of like the popular control algorithms we were talking about earlier, they just kind of threw in some anomalous data and some, or like some anomalous instances and some valid instances, and then checked how, like, just like the likelihood score that it is actually malicious or that it's not. And so that's what they kind of have to check to get the.
Now going on to what they can do in their next steps. So before, like, aside from actually marketing their idea, they could focus on the two things where you can see actual moments of places for improvement. And one is the functionality, because while Zeus does protect against a lot of the control attacks, they don't defend against sensor control attacks, where the sensor data is forged by compromised sensors. And even though they do like talk very highly about what they do protect against, before like selling a product and selling like a security system, you want to make sure that all of your bases are covered. And another place that they could improve on is their vulnerabilities, is that they actually can be attacked themselves. So that's like a huge loophole in this whole process, because they can be attacked by external jammers, which lead to false positives. And we can see that, like, even though the control logic still stays, the incorrect data results is something that if they want to move forward to marketing this product to companies, especially like governments and stuff like that, they would definitely want to fix this area of vulnerability.
And that brings up just one last trade-off, which is that the whole point of making Zeus contactless is that you cannot, by attacking the PLC, you don't attack Zeus, and by attacking Zeus, you don't attack the PLC. But that also means you have to like be ready for different attack vectors for both systems instead of just one system. Yeah, so finally, we just have some discussion points, just like moving on to the future of Zeus, like are the ML models, as we talked about the trade-off between speed and accuracy, like will they be fast enough to detect threats for the system to respond in time? Because this is like large scale infrastructure. If they get attacked, they need to know instantly shut it down. And then also, since Zeus is a separate thing from the system, can it be protected on its own, as Emily said? And then finally, it would be commercially viable to actually install Zeus systems in every ICS, because like ICS systems are like sent out or manufactured on their own, but then Zeus would have to be added to every system on its own. So the cost of that, manufacturing those, but also installing them in every system, especially now you can kind of see it's just kind of like a prototype. They just stuck a microphone on top of a PCB. That wouldn't really work in an industrial environment. So how can that be commercially scaled? Be a point for them.
Thank you.
All right. Great. Extra point for cats pictures. All right, so next group, if you can, did you send it to me or put it on the Google Drive?
Yeah.
Okay, great. Then if you come over here. So questions about the presentation, guys? Anybody else? Any questions? Any comments? You guys can come and set up your review. Oh, we hopefully can do 3. Let's see for this one if we can make it in time. Otherwise, I have to move it to Wednesday, the 3rd one. Sorry about that. But usually we do all the 3 on the same day. Yeah, great presentation, guys. Also the discussion points, yeah, really. So one thing we definitely can do is I encourage you guys to follow up and think more about this, both during the paper creating process. If you want to, you can. You want to put it. So the best thing to do. Okay. So the best thing to do is just upload your PDF onto that folder, so we can just run things from here. Because then the camera and everything is also on this, and we're also recording.
Yeah, that's definitely easier. I'll do that right now.
Hi, my name is Zid Salah, and
I'm Aditya Mishra.
today we'll be presenting the research paper when a tree falls using diversity and ensemble classifiers to identify evasion and malware detectors. So here's our outline. We're gonna first introduce water evasion attacks bypassing malware detection. Then we're gonna go over the proposed solution, which is feature bagging. Then we're gonna present the evaluation methodology. And then we'll discuss the results and interpretations and future work and discussion.
So before we can actually talk about the problem, we're going to talk about the background information a little bit first. So something that's really important to understand is that machine learning is currently being used to identify security breaches. This is actually from a paper from Microsoft. It talks about how machine learning sensors detect, sort, and classify malicious emails and malware attachment. And pretty much this crazy process happens so that automated analysis and predictive modeling can drive stronger and smarter real-time just analysis and determining if the threat is real or not. So this is just something that shows just how widespread the use of machine learning is in malware detection. Currently, almost 98% of all malware detection is done through the use of AI and machine learning, and only 2% is done like by hand using manual inspection. So this is a really good thing because spam and malware from PDFs and apps, which is the primary focus of this paper, pretty much is protected by protects you. Machine learning protects you from that stuff almost all the time without you even realizing it. So machine learning malware detectors operate 24/7 and protect us from bad actors, and this is a really good thing. And for the time being, it is the best system we have, and it is here to stay. But unfortunately, there really are some flaws to this system. Machine learning-based systems are vulnerable to evasion attacks. In particular, they're vulnerable to gradient descent, kernel density estimation attacks, and that's something we're going to be talking about in particular later. So pretty much because of the fact that these machine learning-based systems are vulnerable to gradient descent kernel density estimation attacks, there is serious questions regarding the reliabilities of these systems, and that's a concern that we have to address. And these are two of the example systems that we're going to be talking about.
So in order to conduct the research, we mainly use two softwares, PDF-Rate and Draben, that will help us detect the malicious documents. So first we have PDF-Rate, which is a machine learning-based malware detector that operates on PDF document. It returns a score and or rating instead of a simple benign malicious like just the final result for these submitted files. It is openly available for online attacks and provides considerable information about each submitted PDF. Draben, on the other hand, is an Android malware detector, which operates on software packages instead of documents, and utilizes many string-based features instead of numerical features. It performs a quick scan to extract features from the Android application and disassemble code, like names, values of hardware and components. And it provides a maliciousness score and can identify variables that contribute to the score.
So in general, both of these systems are ensemble classifiers. For example, PDF-Rate is a random forest classifier and is considered an ensemble method as that uses bagging. And ensemble classifiers are pretty much an approach to machine learning that tries to improve performance by combining the results from multiple predictions and using those ensembles as your new value. So if the majority of your votes fall in an uncertain region, and that's what's dictated by this triangle in this graph, your model is then unreliable, at least for those values. If it falls out to the left of that region, it's considered benign, and to the right, it's kind of malicious. So most current malware detection methods use ensemble methods, and for good reasons, because they work significantly better than traditional machine learning models. However, ensemble methods are not perfect. So all of machine learning requires a training data set. And if your classification models encounters new values that are not like anything that that was in your training set, your model will have to extrapolate. And then that's going to be a pretty big problem. These won't be able to effectively determine if something was malware or not. Additionally, classifiers in particular often rely on features that can be mimicked. And there are a lot of features that are used for malware detection. So unfortunately, it's not actually possible to address every single mimicry approach to these classifiers. So what we need to do is actually introduce a mechanism that detects if a classifier performance is decreasing. And so this essentially talks about the general problem of ensemble methods. Your ensemble methods can work great, but if someone were to get deeper understanding of your actual ensemble method, in particular for classifiers, determine where that decision boundary lies, some bad actors would be able to mimic what a benign file is and slip through and get malware onto your system. And this is pretty much a summary of what I just said. The next, something I want to specify is GD, KDE attacks are a massive topic, but for the purpose of this class, we're only going to focus on mimicry and reverse mimicry, which they will talk about right now.
So we have mimicus and reverse mimicry attacks. Mimicus is basically a framework for performing mimicry attacks against PDF-RAID. It implements mimicry attacks by modifying existing malicious documents to appear more like benign documents. It only adds fake elements to the document file, and no existing elements are removed or modified. It constructs these decoy elements by comparing a malicious document to multiple different benign documents. And reverse mimicry attacks, instead of adding content to a malicious document to make it appear benign, it embeds malicious content into a benign PDF, taking care to modify as little as possible. In order to evade detection, it focuses on changing the document structure as little as possible and uses valid PDF constructors to minimize and hide malicious indicators.
And there are some memes that sort of highlight the difference between mimicry and reverse mimicry.
Yeah, mimicry basically adds camouflage, while reverse mimicry makes the malicious elements stealthy.
So essentially, the whole issue is that if anyone gets a deeper understanding of your system, they'll be able to mimic any malware and pass it off as benign software that will infect your computer. So they end up becoming a hacker man, which is not very good. What? So the solution to this is feature bagging. So feature bagging is essentially when individual classifiers are based on subsets of the complete feature set. Essentially, from your overall larger model, you're going to take a random subspace of the features that you're training upon, and then create an ensemble classifier using those random subspace of features. So these classifiers that actually use feature bagging end up becoming significantly harder to evade collectively than a single classifier using all the features. And the reason for that is because once you use feature bagging to create an ensemble classifier, there is no one known decision boundary that is easily identified and mimicked. So therefore, a GD, KDE style attack is infeasible to occur. So that's a really big defense against mimicry and reverse mimicry that we talked about earlier. And this diagram on the right sort of shows how all your different features end up getting bagged and aggregated at the end to create a newer ensemble classifier that has better performance. So now we're going to talk about evaluation methodology.
Yeah. So first we have ARISC, which is the knowledge of classifiers, which is the threat model, and which talks about what we discussed in class for knowing what the attacker knows. So when all of the attributes of the classifier are known by the adversary can slip around 33% of malicious documents and make them seem benign. However, when either of the details of the classifier or the training set are withheld, the attacker's success rate drops to 10% or lower. So here we can see when the attacker knows F, which is the features, T, which is the training set, and C, which is the classifier, he can infiltrate 33 documents out of 100 and make them seem benign. But when less attributes are known, this rate drops significantly to 10% or lower. And we need to talk about adjusting mutual agreement threshold. So before we were using a 50% threshold, which means that anywhere between 25% and 75% of where the document is classified, it will be considered uncertain and will make the classifier look unreliable. However, when the mutual threshold increases to 90%, so only between 0 and 5% we have benign documents, and between 95 and 100% we have malicious documents, then our ensemble classifier will appear much less accurate because we will have a 90% rate of uncertainty. Yet the 5% for malicious and 5% for benign documents will provide more accurate results. We won't have any like results on the edge.
Now we're going to talk about the results and the interpretation of those results. So essentially, the conclusion that we end up coming to is that mutual agreement analysis effectively identifies the samples to be included in the training set as opposed to random sampling. And additionally, feature bagging is actually critical for diversity-based evasion detection, and that's what causes mutual agreement analysis to perform as well as it does. Additionally, strong and private training sets improve evasion resistance. So that's why it's necessary for all malware detectors to obtain a strong and private training set, so no bad actors can try to determine the decision boundary from that. And finally, by including mutual agreement analysis and feature bagging in our models become significantly more difficult to mimic and are thus more resistant to GDKDE attacks. And again, the primary reason for this is because the decision boundary is no longer known, so that no one can easily mimic that decision boundary and pass in malicious data as benign. So now we're going to talk about future work and discussions of this research paper.
Yeah, so we're gonna discuss potential future work. So potential future research would be into the degree to which mutual agreement analysis can improve attack quality. We would also focus on researching the efficiency of identifying malware regardless if the attacker has intel on the way the PDF malware detector works. And we could also research effective ways to determine the ideal threshold that will give us the most accurate results.
So now we have some discussion questions, and these are some questions that we just came up with as we were creating these slides, and were some questions that we just had as we were reading the paper as well. You can see they get significantly more I guess involved as you go down. And the first one was, we were curious about how extensive the effects of PDF malware on a computer can actually be. It wasn't something that we were entirely aware of prior to reading this paper. And we were curious to see just how extensive those effects can be. And additionally, we were curious to see if there's other ways to prevent malware from PDFs besides just using machine learning based malware detectors. And third, we were curious to see if malware in the future will be able to mimic the new decision boundary that happens as a result of feature bagging. And again, we were curious about how it would be possible to actually bypass that new decision boundary in the future. So how would someone create malware that can actually bypass a less defined decision boundary? And finally, we were curious to see if there's a more efficient way to solve this issue than by using machine learning. So that's pretty much it.
Thank
If you
you
have
for
any
your
questions. Yeah.
Thank you, guys.
Okay.
Okay, yeah. I guess it would be too rushed if we do the third one. What's the third? Yeah, sorry guys, can we do it on Wednesday? Wednesday before we start the lecture, you guys can start. So yeah, just before we leave, so again, this is another paper around using machine learning and just generally some smart models in order to detect malwares. And here, basically, features was less of an issue. The biggest question was like, how do we actually collect these different features in order to detect malware? And they also discussed, the concept of evasive malware, right? So the malware that's kind of intelligent and knows that you're using these features in order to detect malware, and then they change their features to mimic that behavior, right? So what happens is, as also like this, one of the questions is, it's kind of like a cat and mouse problem, really, where the attacker knows that you're using this more sophisticated algorithm in order to detect malware. They create the malware to be more similar to that, they kind of evade that, and so on and so forth. So the kind of question is that, will the future be able to mimic this? It's probably yes, unfortunately. And that's what we're doing right now, that, no matter how sophisticated a malware detector is, unfortunately, there is a new way of looking at this problem more and more. But of course, you're trying to make things much more difficult for the attacker. And things like feature bagging, using an ensemble of classifier and so on is usually the idea to make this problem much more difficult. But it's unfortunately it's not same as things like crypto, where you have mathematical guarantees that the attacker cannot really subvert the system. So it's kind of like like the game between the attacker and the adversary. Yeah. Go ahead.
I was a little confused, but so I read this paper and I was confused about the mutual agreement analysis. Like, is that something that they came up with? And then also, did they just edit what PDF Freight and the other software did, or did they like come up with their own?
I think you guys probably can answer this better, but if I remember correctly, so generally where you think that you found malware is a big question, because your model generally doesn't give you an answer. It usually give you some sort of confidence values. And you need to kind of make a decision that, okay, at this point we are attacking, I mean, this is a malware and this is not. And if you remember in the lecture, I also talked about there's this trade-off between your true positive and false positive rate. So you obviously want to detect malware as much as possible, but on the other hand, false positive is something that will bother you. It will be an inconvenience issue. So you kind of need to figure out a way to find this balance. It could be dynamically changed. It could be depending on the application. It could be depending on many other things. And these guys, I think, is also kind of discussing the same problem with different terminology, really. That's, trying to find that balance in a way that you kind of you make the system useful so that it can detect malicious activities. On the other hand, it's not having lots of false positives. You guys want to add something?
Yeah, and also I wanted to add that they went and did a replica of PDF Freight by getting all the features that it uses to detect the malware in order to test it on their end. So it was like a replica of the official PDF Freight software.
Yeah, the PDF Freight, I think, and the other one, the Bree one, there's basically two known malware detector. Could be easily used any other malware detector and do the same thing. They just use those because they're kind of standard at that time. All right, guys. So thank you so much. The next on Wednesday on Thursday we're gonna first do the first presentation and then continue with the lectures.